Hello and welcome to this video lecture. In this lecture, we're going to continue, or maybe I should say pick back up with, our linear algebra review. So this is linear algebra review. And in this case, it's part 2. So we had our first part of the linear algebra review. Then we went into dynamic system modeling using state space approaches. So now we can see why we are interested in understanding linear algebra from a controls perspective, because clearly when we're dealing with these state space approaches, the idea and the ideas and formulations associated with linear algebra are central to what we're doing with state space modeling. So as we saw, so let's just get that in your notes. Linear algebra is central to our state space methods. So going ahead then and diving a bit deeper into what's going on with linear algebra, getting beyond just some of the most basic operations associated, structures and operations associated with linear algebra. Let's now go ahead and dive into some deeper aspects of linear algebra. So review part 2, let's go ahead and start that off with some definitions. So the first definition is a linear equation. And here I'll just shorten that to equation, or EQN. And what is a linear equation? It is a linear combination of, for our class, we'll deal with constant coefficients. Got a little rambunctious there with my n. Of constant coefficients here, and I'll add in for our class. So linear combination of those constant coefficients and variables. Which then are equal to some constant. Here, I'll just go ahead and say constant value. Okay, so we're dealing with what we will call time invariant systems, which means simply that the coefficients are constant. Of course, we can have systems that change in time, in which case then those constants well, those wouldn't be constants anymore. The coefficients would then potentially be functions of time. Now, we're all generally familiar with the form of this kind of equation. So we have, actually, I like IE better instead of EG. So we have a constant A. Here we'll say A1 times our first variable, X1. We'll have our second coefficient multiplying our second variable, both with subscript 2. And then we'll go on off to our last coefficient, AN, times our nth variable. And that can be equal to or is equal to a constant value B, whether B be a non-zero quantity or zero quantity isn't too important right now. Now, one of the things that we have to recognize is to be a linear equation, we can't have any transcendental functions like sine, cosine, the exponential function, etc., or products. Between the different variables. Yep. So we can't have like a cosine of x2. All we can do is have x2. We can't have x2 times x3, not allowed. That wouldn't be a linear equation. We can't have x2 times x2. That wouldn't be a linear equation either. So no products, we just have these coefficients multiplying our particular parameters. So that is going to be, or this kind of structure is going to be what we call a linear equation. When we start talking about a linear system, then we have a set of linear equations. And here I'll again shorten down equations. And that set must be solved simultaneously. And you probably already remember what simultaneously means, but it simply means that whatever we come up with as a solution for this system of linear equations, it must solve, that one solution must solve all of the linear equations at the same time. So what does, another way to say that is, of course, that the same set of, and here I'll just say values, though we'll find that sometimes we may not be able to capture a specific value. But here I'll just kind of use this idea of value being a relatively broad, or value having a relatively broad meaning. So the same set of values for the variables. satisfies each of the equations in the set of linear equations. So, of course, as I already mentioned, that collection of values is called the solution. So here we would be able to write out A11 x1 plus A12 times x2 all the way on out to A1m xm is equal to B1. And so you can see in this case for the coefficients, we have two subscripts, the first one representing the equation that we're dealing with, the second one identifying the particular variable that that coefficient is multiplying. Now we can go to our second equation. So then all the leading subscripts will be 2's for the coefficients. 2m xm is equal to B2. And then we can continue, of course, everything on down to our nth equation, an1 x1 plus an2 x2. And of course, you can see that I am setting this up in a form so close to what we understand our matrix forms to be that clearly we're going to be dealing with matrices here pretty soon. But let's continue to run with this idea of a linear system of equations. And again, you can see exactly why back in our first part of the review, why this idea of matrix multiplication came about the way it did, because we can then see that in forming a matrix and forming a vector of variables, namely x1, x2, all the way to, in this case, xm, we could easily just go ahead and take the coefficient matrix, multiply it by the variable vector. We would, of course, have that equal to the vector of constants that are associated with the b's, and there you go. That idea of matrix multiplication, that kind of what on the surface seemed like a funny idea of, okay, you just kind of go down, you go across the row on one, down the column on the other, take the products, and then add them together. Taking the products probably wasn't so bizarre, but then this idea of adding them together was like, oh, that's a little strange. Why would we do that? But now you can see exactly why we would do it, because that then allows us to express the linear system of equations in a very compact form. I don't have to keep rewriting x1, x2 all the way on out, because the definition of matrix multiplication automatically, or let's say it this way, implicitly encodes in it the plus signs that we have written out for each and every one of these equations. So again, this idea of a linear equation being a linear combination, and understanding that matrices and vectors, of course, are perfect at capturing those linear combinations. So because of how we defined some of the matrix operations, maybe even all of them, they're perfect at capturing that. So you can see this idea of linear combinations coming back in, now applied to linear equations and then systems of linear equations. So with that, let's talk about the properties of the solution. And it turns out that we can say some pretty interesting things about the solution. So the solution may be what is called complete. And here, this means that the system yields a single set of constant values that solves all of the equations. Here we'll just say that solves the equations. But here I'll spell it out. Okay. So that's one possibility, that we just have for x1 through xm, we just get a particular value for x1, particular value for x2, all the way on out to a particular value for xm. We plug in those particular values and those for the x's, and those particular values solve equation 1 and solve equation 2 and solve equation 3 and solve all the equations all the way on out, all the equations associated with that linear system. So that makes things pretty simple. And so there we would have one set, that's the key there, one set associated with the solution, otherwise known as a single solution if you prefer. We can also have infinitely many solutions. And in this particular case, we'll need to use then parametric values. So as you can see, when I'm saying values, I don't necessarily mean that they are going to be constant. So here we may have parametric values. And these are going to be captured by, here I'll just say i.e., they'll be captured by one or more parameters. So parametric values, i.e. parameters, must be assigned to at least one variable in order to form a solution set. So there we're looking at something that on the surface might appear a little less satisfying. We have an infinite number of solutions. But in reality, depending on how we end up at that infinite number of solutions, it isn't that, so certainly we can't come up with a single value, but it isn't that this infinite number of solutions isn't providing value. In some cases, it may not be. So if we have a particular case, and you'll kind of see how I refer to this as, or how I kind of think about this as we go through this class. If we have equations that effectively capture exactly the same information, and then we will have an infinite number of solutions. I'll show you that a little bit later in this lecture. We will have an infinite number of solutions, but those, well, let's say it this way, and that infinite number of solutions really doesn't help us in any way. We already had the information associated with one equation, and it turns out that that second equation effectively just reproduces that very same information. That doesn't give us, it gives us infinitely many solutions, and it really doesn't help us in any way because it's just a repeat of the same information that we had. So as I was indicating, I kind of like to look at these equations from an information perspective. If you are, if you will give me that latitude. On the other hand, though, sometimes we may end up with infinitely many solutions, but those solutions are less complex. In the term of linear algebra that you may have heard of before, the solution space spans fewer dimensions than what we were originally dealing with. And so what does that mean? That means that we actually got some valuable information, albeit we weren't able to get down to a single solution, but at least we were able to say, hey, something over here isn't a solution, something over here isn't a solution. We can't say exactly what is a solution, but we can at least say the solutions have to fall in this particular space, and anything outside of that space just can't be considered a solution. And so that does give us quite a bit of value. I will probably mention this a couple times throughout the class, if not more than a couple times. One of the nice things about being an engineer, of course, is that from a mathematical perspective, when we have an infinite number of solutions, that infinite number usually goes off to, the space associated with that infinite number of solutions typically goes off to infinity. We as engineers thankfully have something else at our disposal, which are bounds, because we know that the physical systems that we're dealing with, the mechanical systems that we're dealing with, just can't go off to infinity. It doesn't work. And so if we end up with a mathematical solution that has, or a mathematical expression that has infinitely many solutions, we as engineers can then start to say, okay, sure, that represents maybe a space like a line, which is infinitely long. We can then start applying a little bit of common sense to that and saying, well, we can chop off the line at one end because of some parameter that just can't go that far. And we can chop off the line at the other end. And then we end up with, albeit still an infinite number of solutions, we end up with an infinite number of solutions along a line segment rather than along an entire line stretching off to infinity, potentially in both directions. And so if our solution space was that line, we as engineers can then trim it down even more, thankfully. So that's where we have a little bit of an advantage as as engineers in general, mechanical engineers in particular, potentially. So we have a single solution, we have infinitely many solutions. We may also have the case where we have no solutions. And here that means that no set of values here I'll say constant or otherwise, meaning if we wanted to try to work with this from a parametric perspective, can be used. That'd be nice if I didn't stick an E on the end of used where it didn't belong. Can be used to form. So nothing can be used to form a solution set, something that simultaneously solves all of the equations. Now, in this particular case, because we have no valid solutions, this is called an inconsistent, or the system would be called an inconsistent system of equations. And why does that name inconsistent actually make some decent sense? Well, I'll get it down in your notes in a moment. Let's get down system though of equations. So what does that mean? If we look at these equations, and each equation giving us either some kind of constraint or some kind of information, what this is essentially saying is it's saying that some of the information we've been given, or some of the constraints, one or more of the constraints that have been imposed on us by those expressions, don't match up. And so since they don't match up, you can come to the conclusion that the information that's being provided to you isn't working out. Somebody is wrong in some way. And so that's one way of looking at it. Or it's saying, if we're looking at these as constraints, it's saying that given those constraints, there's no way you can get whatever needs to be done while satisfying all of the constraints associated with the particular equations that we're dealing, or that we have been given for that system. So if that last case is called inconsistent, you can imagine that these first two cases are called consistent. And that means that the information or the constraints are consistent with each other. So we don't have something that's pushing us out, and or some information that is wrong causing us trouble. So here I like to say that this possibly means, so there are a variety of ways of interpreting this, I'm sure. So I'll say, among other things, because I don't want to rule out other possible interpretations. So if we're looking at those equations as capturing constraints that are associated or applied to the system, it means that we clearly can't get the system here. I'll say to do something, namely to meet all of those constraints simultaneously, at least not in its current state. And so the way I like to refer to that is that you can't get there, wherever that get there means in the context of those constraints. You can't get there from here. Because you've just imposed too many constraints that pushed the system in too many competing directions, and in the end, you just can't develop a system that would meet all of those constraints. Another way that so that's a kind of a constraint side of things, saying that this, whatever our system is, must satisfy this linear equation and this linear equation and this linear equation all at the same time, and it just doesn't work out. we're over constraining. That's another distinct possibility, that you're over constraining the system as well. Looking at from an information perspective, we are getting some bad information. So the information in some set of the equations is perfectly fine, but one or more of the equations is giving us information that isn't matching up. Another thing that we could be running into is that the system itself is inconsistent. No, not inconsistent. Inconsistent. There we go. And of course, this could mean that it's giving us different results. At different times. So maybe we have a system that wasn't built terribly well. We have some misalignments associated with tolerances and gaps and things like that. And so when we run the system once, because things are in one position, we get one set of results, and then we reset the system, but in so doing, maybe some different gaps are forming and the other gaps we had are closing up, and now the system's going to behave slightly differently. And so we might be getting different information from our system at different points in time for different runs, as an example. So let's go ahead and take a look at solution sets for a simple set of linear equations, specifically just a set of linear equations where we're only dealing with two variables. That would, of course, be considered essentially a two-dimensional system that we're working with. And we'll look at the solutions associated with this system from a variety of different perspectives. So we're going to rework the same problem several different times, and then we'll take a look at some variations on that same problem a couple more times. So let's go ahead and take a look at this to start to, or this simple system, to start to see if we can understand what's actually happening with this idea of these different types of solution spaces. So this example is going to again run through multiple parts. So let's find the solution set. Again, if any, because remember, we only have three possibilities for these linear systems of linear equations. Now, the key here is, again, linear equations. That is an important understanding of what we're dealing with here. So let's find the solution set, if any, for the following set of linear equations. Specifically, the following two equations for lines. Now, of course, there are different ways of representing equations of lines. Here, I'll just have x plus 2y is equal to 6. And I guess I'll give myself an and here. 3x plus 4y is equal to 8. Now, usually we didn't generally work with equations for lines in that way. A little hard to interpret what's going on. So let's go ahead and just rearrange things a little bit. And we would have, so solving for y, we could have y is equal to negative 1/2 x plus 3. And because remember that and still applies, y is equal to negative 3/4 x plus 2. So of course, since we have that and there, these are simultaneous equations. And the easiest way to envision the solution to these simultaneous equations is that the point of intersection of these equations would be the single point, if we even have a single point, would be the single point where both equations would be satisfied by the values associated with that point. So let's go ahead and see if we can find that particular point. So of course, graphically, we would just, and I'll draw this, up a little bit later so that we do get the graphical interpretation that I just briefly mentioned. But of course, another way that we can solve simultaneous equations is to eliminate the variables. So eliminate a variable and then keep solving, potentially eliminate another one. In this case, we wouldn't need a second elimination. So let's go ahead and work through that approach. Let me skip down one more line. That looks good. So here, let's, as I indicated, do what you may have first been taught to do when you ran into simultaneous equations. So let's start way back with probably your first approach, which was to eliminate variables. Here we could just say, thankfully, we already solved for y, so we could just say the y from one equation is equal to the y associated with the other equation. And when we do that, we get a negative 1/2 x plus 3 from the first equation is equal to negative 3/4 x plus 2. You get my plus sign in there first. Plus 2 from the second equation. And then going ahead and isolating the x's on one side and the constant terms on the other side, we can quickly see we will end up with a 1/4, recognizing, of course, that 1/2 is just nothing more than 2/4. So we end up with a 1/4 x is equal to -1. Otherwise, we can otherwise say then that x is equal to -4. Once we eliminated the variables, though, or one variable, and found the other, we then had to go back, of course, and find the value associated with the other variable that is consistent with the value for the other variables, in this case, the other variable that we found. So here I just elected to use the second equation since we had a 4 in the denominator and x turned out to be -4. So that made life a little bit easier in terms of canceling out those 4s. And pretty quickly, you can see that we would end up with y is equal to 5. And so that would be our solution set for this particular, or our solution for this particular set of simultaneous equations, -4 and 5. So single solution, and we're set to go. Now, when we are looking at working with these two equations, here I went ahead and did my, worked through my relatively standard algebra and came up with my, equations and for y in terms of x, and then went through the substitutions that I needed to, the equating and substituting, in this case, really just equating and then solving those equations. I could have, though, if I elected to, worked with the equations directly. I could have multiplied by a constant all the way through. I could have added one equation to another or subtracted one equation from another, provided that I did it throughout the entirety, the entirety of the equation. And I could have used that as a way to eliminate a particular variable if I'd wanted to. So of course, you could immediately see that one thing I could have done is multiplied the first equation by -2, and then I could have added it to the second equation. And then clearly I would have gotten a -2x plus 3x. Well, that's just x. I get a -12 plus a +8. That's just -4. And then I could have arrived at this expression pretty quickly by working with the equations kind of as entities in and of themselves and doing then operations across the entire entity, if you want to think about it that way. That, of course, is meant to lead us into the next part of the example, where I'm going to use exactly the same values. So let's go ahead and find the solution set for the following augmented matrix. Now, of course, what's an augmented matrix? Well, what we can do is we can go ahead and capture the coefficients, 1, 2, 3, and 4. We can capture the constants, and we'll separate the constants from the coefficients using a dashed line. So here, these are the variable coefficients. And these are the constants. And this is combined in one matrix. Let's say one augmented matrix. There we go. And it makes sense that we would have to separate these numbers using this line because, or that dashed line, because we don't want to confuse ourselves between these fairly different quantities, so to speak. Because if we got rid of the line, we wouldn't have any idea that there is a fairly important difference, a fairly important distinction associated with what's on the left-hand side of the matrix versus what's on the right-hand side of the matrix. Clearly, you can see based on my matrix multiplication, if I wanted to have a variable vector where the first variable is x and the second variable is y, we can then see that the first column just represents the coefficients. Well, let's just say it this way, the x coefficients. And the second one represents, of course, the y coefficients. And again, we're seeing how this idea of matrix multiplication, the idea of vectors, etc., how all of this is captured very, very conveniently, very compactly, using this matrix multiplication that is excellent at capturing these linear combinations in a very efficient fashion. So we can then, remembering back, use what are called row operations to help us solve this particular problem. So with row operations, we can multiply a row by a constant. We can add or subtract the multiple of one row. To or from another one, another row. Wait, but wasn't that exactly what I was mentioning up here? If I multiplied the first equation, i.e. the first row, by -2 and then added the two equations together, and of course I would multiply by -2 because that would give me a -4y in one equation, a +4y in the other, and when I add the two together, of course, what's going to happen, those would cancel and I would just be left with x in the resulting single equation. Well, that's exactly what this is right here. So we can see, of course, that these row operations, when we're looking at them in this way, could have just been applied, as I indicated above, directly to the equations themselves as entities. We just have to make sure that we apply it across the entirety of that equation. In this case, across the entirety of the row. Okay. And as you can imagine, it doesn't matter whether I write the first equation first and the second equation second, or the second equation first and the first equation second. Doesn't matter, the information is the same, so we can of course exchange. Now we'll see, of course, later in this class that changing the order of the rows can impact things, but for right now, in terms of just capturing the information that we're interested in, we can exchange the places of two rows, and we of course haven't altered the information that is captured by those equations in the least. And so that's something else that we can do. So let's go ahead then. So we have our augmented matrix. We've kind of gone through a little refresher of what augmented matrices are, and that we can perform these things called row operations on this matrix. And so let's go ahead and do exactly that. So let's go ahead, and here I'm going to do things in a bit of a different order. So we already talked about maybe an order that was a little bit better for more efficiently arriving at a solution that we could clearly identify just by looking at the equations, i.e. multiplying the first equation by -2 and then adding it to the second equation. But it turns out that when we're talking about matrices, and of course matrices are perfectly built for computers, when we start talking about matrices and computers, we don't really necessarily want to try to rely on computer code being able to go through and identify some shortcuts that would get us to a solution more rapidly than, which is something we as humans could easily identify. We would rather just have a straightforward approach to solving the same problem the same way every time, regardless if there's an obvious way of making things a little bit faster, at least obvious to us as humans, to make things faster. Now, if there was something that was obvious to us as humans, what could we do? We could enter the data in differently to take advantage of that, the obvious thing that we can see as humans, but of course would be completely invisible to a computer, because we want a computer to just march through a set of steps each and every time and give us consistent results, of course, each and every time. And so that's what we're going to do here, is we're going to actually march through in a specific way to get to particular forms that are important from a linear algebra perspective. So the very first thing I want to do is I want to take everything. So I want to have all of my ones as far up as I can. And by far up, I mean as far to the left as I can. So any leading, what we call leading ones, I want them as far left as possible. So here, thankfully, I actually have a leading 1, 1, 2. So we're set to go. And by leading, I mean that everything to the left of that 1, in this case, there's no entry to the left of the 1. But if I had any entries left to the 1, in order to be a leading 1, all those entries would have to be 0. Now, we only have one leading 1 for this particular problem. So what do I want to do? I want to take all the entries that are below that leading 1, and I want to make them 0. So I want to make this next row, the first entry in the next row, 0. And if I had any more rows, I'd want to make those 0 too. So how do I do that? Well, clearly we started with a 3 in the second row. And so couldn't I multiply the first row by 3 and then subtract the first row from the second row? And of course, that would give me a 0 there. What else would it give me? Well, if I multiply this by 3, I get a 6 here. And I take that 6 and I subtract that 6 from 4. So what do I get? Clearly, I'm going to get a -2. And then additionally, what am I also going to have? Well, I'm going to have 3 times 6. Well, that's just going to give me 3 times 6 is going to give me 18. And then taking that 18 and subtracting off from 8, I'm going to get a -10. So we can then see that I've managed to get this first entry in the second row to be 0. And I did that simply by subtracting. So here we'll just write subtract 3 times the first row from the second row. And so that's what we end up with. Now, of course, for that second row, I don't yet have any leading ones, but that's what I want, is I want the first non-zero entry to be 1. Well, that's pretty easily managed. So what I'm going to do now is, if I want to take that -2 and turn it into a 1, I'm just going to multiply by -1/2, otherwise known as dividing that second row by -2. So I'm not doing anything to the first row. That one I can just write straight on across. And then for the second row, 0, and then -2 divided by 2 is 1. And then -10 divided by -2 is clearly going to be 5. And so I got to this by dividing. Here, I'll just write it out as divide the second row by -2. Now, this is a pretty important structure because one of the things that you can immediately see, and maybe you even caught on with what I have up here with y is equal to 5, you can immediately see that 0 times x is 0 plus 1 times y is y. So all I get is y, and that's equal to 5. And so I can immediately see that I get y is equal to 5. And then in this form, what could I do? I could substitute that 5 back in for y into the first equation, and I could get 2 times 5 is 10, and I have 1 times x, so I get x plus 10 is equal to 6. Well, I just subtract 10 off of both sides, and I get x is equal to -4. And so I can easily use this particular form to back substitute to find a value, and then keep back substituting that value in to finally solve the system of differential equations. So let's go ahead and capture. So note this structure that we've been talking about, where every non-zero row, now we'll talk about zero rows, rows of all zeros here in a second, but where every non-zero row in the coefficient section has a leading, a leading one for the first non-zero entry in, oops, my n got a little off there, in that row. And this leading one is further to the right as you move down the rows. So remember, we're describing a particular form here. And any rows where all coefficients are 0 are moved to the bottom of the matrix. So if you encounter a row of zeros, you just move it to the bottom. and you can just, as soon as you encounter one, you can just keep moving it to the bottom, moving it to the bottom. You can move the other 0 rows up because it doesn't really matter at that point. Because all we need is just a collection of all 0 rows at the bottom of the matrix. And this in particular let's move it out indentation wise. I guess I'll move it out just a little bit. So this in particular is called row echelon form. And to introduce another term, so you may have been exposed to row echelon form already, and another term, the process used to arrive at this form is called Gaussian elimination. And so you can see how simple it would be to work through that. You just have some computer code from a computer perspective, that is, and even as a human, right? So the wonderful thing is you would just sit there and take all the 0 rows to the bottom, and as soon as you get another 0 row, you just move it to the bottom. But meanwhile, you're just sitting there taking the leading value, making sure it's a 1, making sure that all leading values move further to the right, of course, as you get further down in the rows, and then taking that leading value, multiplying by the inverse of that leading value to get it to a 1, and then continuing the process. So it would be fairly simple to code this particular process up in software. Now, to get to another form, though, I could do one more thing, which is instead of having zeros below the leading ones and only requiring the values below, or the entries below the leading one, to be zeros, I could add an additional requirement that the values above the leading ones must also be 0. So if I do that, going back up to the matrix appearing at the top of the screen, I can see pretty clearly that what we're dealing with is we have that 2 above our 1 that's appearing in the second row. And so what I can do is, of course, I can multiply the second row by 2 and subtract it from the first row, in which case I would get 1 times 2 is 2, subtract that off of 2, of course, I get a 0. 2 times 5 is 10, subtract that 10 off of that 6, and I'm, of course, going to get a -4, which is exactly what you would expect. So I can then end up with 1001. We'll talk more about that structure. We'll talk a lot more about that structure throughout the course, but we'll talk more about that structure here in a moment. And then, of course, I end up with a -4 and a 5 for the augmented portion of the matrix. Now, clearly, if I take that 1 and say, oh, that represents what's multiplying x, so I get x plus 0y is equal to -4, obviously, then that means that x is equal to -4. And then 0x plus 1y, otherwise just known as y, is equal to 5. That means that my solution can just be read off of this as -4 for x and 5 for y. So you can see the convenience of this particular form. So let's subtract 2 times the second row from the first row to get this particular form. So let's see what that does for me. So, well, I shouldn't say let's see what it does for me. We already know what it does. I'll go ahead and write that down so I know I talked you through it. We'll write that down more formally here in just a moment. But let's go ahead and since we know this form does something good for us, we're going to go ahead and say that this is, or let's describe the structure. So note the structure where there is also zeros in the other entries of a column. That contains a leading one that's now called reduced row echelon form. And of course, that augmented process has its own name. So the process that produces this form may sound familiar to you is called Gauss-Jordan elimination. So of course, as we know, the first column captures, of course, the x coefficients. The second column captures the y coefficients, or the coefficients of y. And then the last column captures the constants. And we'll talk a little bit more about the constants a bit later in this lecture. And so then for us, we just end up with 1, 0 for this reduced row echelon form, 1, 0 for the x coefficients, 0, 1 for the y coefficients, negative 4 and 5. And I talked you through this. This, of course, then leads to 1 times x plus 0 times y is equal to negative 4. And then we have, I'll go one line down, 0 times, no, not y, that would be bad. 0 times x plus 1 times y is equal to 5. So if we didn't know to just read off the solution, we could go ahead and capture it in this particular form. And so then, of course, that means that the solution for us is just simply, or can be captured in particular, using this idea of vectors. So the solution for this part is simply x, y is equal to -4, 5 as before. So we can then see that we can just equate the variable vector now to this vector of constants, which indicates the values of those variables that will solve both of those equations. So now let's go ahead and look at a more formalized way of representing this this information in the augmented matrix, because the idea of having an augmented matrix is fine, and it's a perfectly valid way of working through trying to solve this problem, but it isn't exactly following the or falling within the intent of what we're trying to do with matrices and vectors, because we're combining together these quantities that are doing different things into a single matrix, and then we have to do this kind of interesting stuff at the end, so encoding everything into that single matrix and then decoding everything from that matrix in the proper way. So let's go ahead and then work with a more I'd say regular, maybe even more formal might be a better way to call it, a more formal way of working with matrices and vectors. So here we have a matrix equation that we want to solve, where, of course, our two simultaneous equations are encoded into that matrix equation. So here we'll have 1, 2, 3, and 4. Now, of course, we know that those are the coefficients multiplying x and y, and so we can capture that as x and y. And if we multiply that out, of course, you'll get 1 times x plus 2 times y for the first equation, and we'll get 3 times x plus 4 times y for the second equation. And of course, then we have to say, oh, okay, well, those are equal to the constant vector, or the vector of constants, 6 and 8. And there we go. We can see now that we've completely encoded all the information that was in the simultaneous equations, and there's nothing implicit about it, unlike in the augmented matrix. Here, everything is right there. We just go ahead, follow our standard matrix multiplication operation, or work through our standard matrix multiplication operation. We completely recover our original simultaneous equations. So now, how can we work with this particular expression? So we can solve this equation by multiplying both sides of the equation, and this time I'll shorten equation, by what are called elementary matrices. Now, remember, it's important to note how I am going to multiply by these elementary matrices, because you can multiply one side of things or the other side. So in our particular case, we'll multiply by those elementary matrices on the left. Okay, so now we need to understand what in the world these elementary matrices are. So going ahead and defining an elementary matrix. So an elementary, or here I'll stay with the plural. So elementary matrices. And here I'll give the symbol, or give them the symbol capital E, are formed simply by performing the desired row operation on the identity matrix. There we go. So we got this idea of the identity matrix coming into play here. So what is the identity matrix? Well, as is true with everything that is captured by the idea of identity, it turns out that multiplication by the identity matrix of course, using the matrix multiplication operation that we defined before. Remember, it was a definition. So where multiplication by the identity matrix I returns, as does all identities, simply returns the subject matrix itself. So let's get that down. The subject matrix. Now, there's an interesting property associated with the identity matrix. So A times I, it turns out it doesn't matter what side we multiply the matrix on by the identity. We can multiply it on the right side, on the left side. Either way, it returns the original matrix. And the identity matrix has a particular form. So the identity matrix has the following form, has a form of I is equal to 1, 0, 0, 1, then zeros all the way on out, zeros all the way on out, zeros, zeros, all the way over to our last entry, which is a 1. So clearly we have zeros everywhere except on the diagonal, and then the diagonal has all ones. So note, this of course is an n by n matrix with ones on the diagonal. So now we can use this idea of the identity matrix, this idea of elementary matrices, to go ahead and manipulate what's happening with this particular expression. So as we already know, we want to subtract 3 times, as we pretty much have we did in part B, we want to subtract 3 times the first row from the second row. So let's see how we can do that. So to subtract 3 times the first row from the second row, then what would we do? Well, we would just go ahead and say, since this is our first elementary matrix, let's just say that that's E1. And E1 is going to be my identity matrix, except to subtract 3 times the first row from the second row, we need a -3 there. And it turns out that we just have a 0 up in the upper right-hand corner. So let's see how that works. So then we have 1, 0, -3, 1. We have 1, 2, 3, and 4. All that multiplied by xy. And so we can see how this is going to modify what's happening with my expression, because this -3, so I have 1 times 1 is just going to give me a 1. 1 times 0 is going to give me a 3, and add that together, so I'm just going to get a 1. Then over here, I'm going to get clearly just a 2, so that just reproduces the first row in the matrix once I multiply everything on out, because I'm going to get a 1 plus 0 to get a 1, a 2 plus 0 to get a 2. But then when I get to the second row, what happens? I'm going to have a -3 times this 1. I'm going to have a -3 times this 2. And then I'm going to add that to this 3 and this 4. Well, that's nothing more than taking 3 times the first row and subtracting it from the second row. And so we can see exactly how that works. So -3 plus 3 is just going to give me 0. So we already know that this is going to, the first row will just reproduce the first row, or multiplying through the first row. And then I get a -3 plus 3, that gives me a 0. And then I get a 2 times -3 is -6, plus 1 times 4 is just -6 plus 4. That's -2, just like we had before. And of course, this is all multiplied by xy. Okay, so that captures that. That's what's going on the left-hand side. Now on the right-hand side, what do we have? We have, because we have to do the same thing on the right-hand side that we did on the left-hand side, so we need to multiply my constant vector by 1, 0, -3, 1. And that's all multiplied by 6, or that all multiplies 6, 8. And so when I do that, what do I get? Well, I clearly get a 1 times 6 is 6, plus 0 times 8 is just 6, so that is unchanged. Then I get a -3 times 6 is -18, plus a 1 times 8, that gives me that -10 again. There we go. And so that just comes right on through there. So now let's go ahead, because I do want to actually go through solving this particular problem. So then here I'll just say, for the remaining operations, what do we need to do? Now, got a little S in there, my apologies. So for the remaining operations, there we go. what do we have? Well, remember that I needed to divide. So here, I'll just write it way over here. So I need to divide the second row by -2. Here, I'll just squeeze in the -2 there. So how do I do that? Well, that clearly is associated now with E2. So remember, E1 was the 1, 0, -3, 1. So now E2 is what? E2 is simply 1, 0, 0, -1/2. And that will end up scaling that second row. So let's see that for sure. So here we'll start with the left-hand side. So I get 1, 0, 0, -1/2. And then I have that multiplying 1, 2, 0, -2. Of course, that then all has to multiply x, y. And so going ahead and multiplying that out, clearly I get 1 times 1 is 1 plus 0 times 0 is just 1. 1 times 2 is 2 plus 0 times -2 is just 2. So that first row is simply reproduced just like we wanted. Now what's going on with the second row? Well, second row, clearly the 0 in the second row is going to wipe out everything in the first row of the next matrix. And so we're just going to get -1/2 times 0 is 0. And the -1/2 times -2 is just going to give me a 1. And there we go. And of course, all of that times xy. And that's equal to then the right-hand side. So now I need to do exactly the same with the right-hand side. 1, 0. I need to left multiply by this elementary matrix. And I have 6 and -10. Clearly, the first multiplying through by the first row, that's just going to give me my 6 on back, just like it did before. The second row is going to be different, of course, and that, so 0 times 6, the first entry in the constant vector isn't going to do anything because I'm just going to get 0 there, plus 1/2 divided by -10 divided by -2, and that's just going to give me 5. And so again, you can see the same thing forming, because if we got rid of the x, y, and the equal sign, and just kind of put everything together as an augmented matrix, that's exactly what we had before for our augmented matrix. So you can see the efficiency associated with the augmented matrix is I'm not constantly rewriting x and y. I'm not constantly rewriting the equal sign, but that's okay. That's a relatively small price to pay to have this very formal way of representing what's happening. So now let's go ahead and go through the final operation, which is let's subtract 2 times the first row from the second row. And so when we do that, we have E3 is equal to 1, -2, 0, 1. So that will produce that particular effect. Let's see how that works. Now, again, this is us running to what would effectively be called reduced row echelon form. So multiplying by that, but you'll see very shortly why I'm interested in doing that. Let's go ahead. Actually, I'll go down. I'll go in the middle. Since I can't decide where I want to go, I'll just go in the middle. There we come on. There we go. And so then we will have, and then I went middle too low. You got to love that. So I'll go in the middle here. There we go. And so we'll have 1, -2, 0, 1, all that multiplying my 1, 2, 0, 1. Now, clearly, this is going to leave the second row unaltered. So we'll have our xy. So the second row just comes straight on across, exactly like we wanted 0, 1. Now, what's going on with the first row? So the first row, I have 1 times 1 is 1. I don't know why it's doing that. 1 times 1 is 1. -2 times 0 is 0. So add the two together, I just get 1. But here's the key. So the next one, and let's see here, the next one is what? Let me move this up. We have 1 times 2 is 2, plus 1 times -2 is -2. Clearly, that's going to give me 0. And then I just get xy. So there we go. We have the identity matrix, and having the identity matrix there isn't something that just happened by chance, as you will see here momentarily. That's exactly what we were expecting, which is why I wanted to push this example, this one step further to what we would have considered reduced row echelon form using an augmented matrix. So nonetheless, though, we need to, and I guess I should have an equal sign here, kind of continuing on around. So if you can put in those additional equal signs there, that'd be nice. Then last but not least, we have this 1, -2, 0, 1 multiplying x, no, not xy. In this particular case, 6 and 5. 6, 5. And so this, of course, is equal to, so the second row of the constant matrix will just come right on through, as we can see with this 0, 1 here. The first row, though, which is the one associated with the 6, what am I going to get? I'm going to get a 6 times 1 is obviously 6, plus a -2 times 5 is -10. So 6 minus 10, in essence, is -4. And so again, multiplying that vector, that xy vector, by the identity matrix. So then we have 1, 0, 0, 1, and understanding what the identity matrix, and you can go ahead and multiply it out, and you'll see immediately that, of course, you will just get the original vector back. And that original vector is then just equal to our constant vector, -4 and 5. And there we go. We have the values that we know, that we've seen. We'll solve that set of simultaneous equations. Now, as I mentioned before, this idea of multiplying in this particular fashion and having that sequence of matrix multiplications end up at the identity matrix was not by accident. That's what these elementary matrices are doing. They're reformulating things, and if we've done stuff right, they're reformulating things so that we will then end up with an identity matrix once we multiply everything together. So let's go ahead and see how that works. So what do we have? We already have our 3 elementary matrices, E1, E2, E3. Now, for simplicity, I'll go ahead and just take E3 and leave it as E3 for right now, because I just want to focus on the first 2 matrices, 1, 0, and then 0, -1/2. So that's going to be, of course, E2, or that comes from E2. And then what do we have? For E1, we have 1, 0, negative 3, 1. So you will recall that being E1. So let's go ahead and rewrite now E3, and then I'll write the result of the matrix multiplication of E1 and E2. So E3, you might recall, was 1, negative 2, 0, 1, and that's E3. And then let's go ahead and multiply out E1 and E2. So we get 1 times 1 is 0. 1 times 1 is 1 plus 0 times negative 3 is 0. So clearly, we're just going to have 1 plus 0 is 1. We will have 1 times 0 is 0. We have 0 times 1 is 0. And so 0 plus 0 is just 0. And then for the next row, there we go. We have negative 3 times 1 is negative 3. Oh, sorry. I'm getting myself messed up. We have, there we go. We have the second row of E2, 0 times 1 is 0. We have negative 3 times negative 1/2. That's just positive 3/2. There we go. And then last but not least, the second row of E2 times the second column of E1, we get 0 times 0 is 0. And then we get negative 1 time, or sorry, negative 1/2 times 1 is just negative 1/2. And there we go. So that's the product of E2 times E1. So now multiplying through by E3, what do we get? So we get 1 times 1 is 1 plus negative 2 times negative or positive 3/2. That's just going to give me a negative 3. And so then I'm going to just get a negative 2 here. Then we're going to have 0 times 1 is 0. We're going to have a negative 2 times negative 1/2. Well, that's just going to be a 1 when I add those together. Then going to the second row for E3, 0 times 1 is 0. 1 times 2/3 is just 2/3. And we can just see that, of course, the next entry will just be negative 1/2 because of that 0, 1 associated with E3. So the 3 multiplied together will just give me negative 2, 1, 3/2, and negative 1/2. So as you might expect, I've now, instead of just multiplying my coefficient matrix individually by these elementary matrices, now I'm just multiplying all the elementary matrices together in the proper order. And so then we can take, so instead of dealing with the equation the whole time, we can then just take at the very end this product, the sequence of products of those elementary matrices, and we can just multiply the coefficient matrix by that 1, 2, 3, 4. And what do we get? And of course, this won't be a surprise. We're going to get the identity matrix, but let's just check it out. We get negative 2 plus, so for the first row of my my products of the elementary matrices, I get negative 2 times 1 plus 3 times 1. That obviously is going to give me a 1. Now for the next row column, we get negative 2 times 2 plus 1 times 4. Well, that's negative 4 plus 4. That's obviously going to be 0. Going down to the next row, the second row for the first matrix, I get a 1 times 3/2 is just 3/2 plus a negative 1/2 times 3 is a negative 3/2. That's just going to give me 0. And then last but not least, I have the second row in the second column. 3 halves times 2 is just 3 plus a negative 1/2 times 4. That is just a negative 2, and I get a 1. And sure enough, I end up with an identity matrix. So this is the original coefficient matrix. Here we'll just call it A, and we take those products, the overall product of the elementary matrices, multiply those together, we get a 2x2 identity matrix. And that allows us to now introduce another concept, very important concept in linear algebra. Any matrix that when multiplying another matrix, A results in the result of that multiplication is the identity matrix. Then that matrix is called, that matrix that is multiplying A is called the inverse. Oops, got a little wacky with my V there. It is called the inverse of A. Oy, sorry, getting a little rambunctious with my writing there. The inverse of A, and it is given the symbol A inverse. There we go. And it turns out that the inverse has an interesting property as well. We just saw that, of course, A inverse times A, because the products of those elementary matrices exactly fits that description. So that product of the elementary matrices is the inverse. And so A inverse times A, of course, is equal to the identity matrix. So if I do left multiplication, I get the identity matrix. Turns out if I do right multiplication, I get the identity matrix as well. So that's one property of the inverse that's very interesting. And I know I said it, but let's go ahead. And in this case, E3 times E2 times E1, of course, is equal to A inverse. So we now have this understanding of the identity matrix. We have an understanding of an inverse. We have an understanding of elementary matrices that perform a certain single row operation on a particular matrix. So you can see a lot of the concepts that are central to linear algebra coming into play here. So let's now go ahead and rework variants of that example. So I worked the same example 3 different ways, one going with simultaneous, standard substitution approach for simultaneous equations. That was probably the first approach you learned, and then going into this idea of using an augmented matrix, and then last but not least, using the idea of the elementary matrices and a matrix equation to work with a matrix equation that would then allow us to solve that. So each one of those allowing us to solve that set of simultaneous equations. Now, we also mentioned, so in each case, what did we have? We had a single solution. We also discussed the fact that, and let me see, where have I been putting those all the way over? Kind of more, a little bit further in. Let me put that D a little further in, my apologies. But I'll give it a few lines, a couple lines, so that way we know we're starting a new part of the problem. So now let's go ahead and take a look at a couple situations where we either have an infinite number of solutions or we have no solutions. So we're going to now fundamentally change the problem. So let's go ahead and work with the following augmented matrix. And in this particular case, we'll run with everything being the same. 1, 2, 6, 3, but I'm going to change that 4 now to a 6. 3, 6, 8. Now, of course, you're probably potentially already seeing a little bit of a spoiler here, but just work along with me if you're seeing it, and if you're not seeing it, you'll see it here in just a second. So now a 6, and it was a 4 before, just, so that you make sure, we make sure that you note, or I can make sure you note that change there, that fundamental change in the problem, because we can see, and here again, I'm working with an augmented matrix. We can now see that if I subtract, don't get my T in there yet. If I subtract 3 times the first row from the second row, what do I get? Well, it turns out now that the second row, and that's what I was saying, you probably already saw it, the second row is now a scalar multiple of the first row. And so what do we get? We get 0 to 6, and because that remains unchanged, but then I get, well, I shouldn't say for the coefficient matrix, it's a scalar multiple. And so then I get a -3 times 1 gives me -3, and I add it on, so that gives me 0. -3 times 2 gives me -6, add that on to 6, I get a 0. -3 times 6 is -18 plus 8, that gives me a -10. And there we go. So in the coefficient side of things, we now have a row of zeros. Of course, we need to put that row of zeros at the bottom. We can also see something interesting though, because this then indicates that, because remember, we can take that coefficient matrix and multiply x and y, the x and y vector, by that coefficient matrix. So we get 0 times x for the second row, 0 times x plus 0 times y. And look at the constant matrix, or the constant vector. We get a -10 is equal to -10. So we can then clearly see that 0 is not equal to -10. Here I'll say clearly 0 equals -10 is wrong. And that means that this system is, of course, inconsistent. The first equation is telling us one thing. The second equation is saying, nope, that's not right. And since we don't know which one's right, all we can say is somebody, maybe both are wrong. Who knows at that point? Or if these are constraints, we can say, yeah, we can meet the first constraint, but there is no way we could ever meet the second constraint while meeting the first constraint. So we can see that that's an issue. So that means, of course, that there is no solution that satisfies both equations at the same time. Oop, that he got a little scrunched. So as I indicated, we can see this in the numbers in the structure of the coefficient matrix and the constant matrix, if you'll let, or constant vector, if you'll let me decompose the augmented matrix into those two parts. But we can also see this graphically. So this can be seen by plotting the equations of the lines. So the first problem that we were working with, we'll just go 1, 2, 3, 4. Let's go a little bit more. There we go. So if we have the y-axis at 2, 4, 6, and 8 for y, I'm going to avoid writing the, I guess I'll put the 2 down below because we're going to have a little action there. And of course, here we have our origin. Then we're going to have -2, -4, -6. Here, I'll just label -2, -4. And then on this side, negative or +2, +4, +6. For our original case, what did we have? Well, we found out that the two lines intersect at -4 and +5. If we, though, go ahead, well, let me rewrite those equations. So what do we have? We have y is equal to -1/2 x plus 3. We have y is equal to -3/4 x plus 2. So looking at the slope with a rise over run, a rise of 1 and a run of 2, but of course the negative slope means we're dropping. Let's do that one in red. That means that we go over 2 and we drop 1. We go over 2 more, we drop one more. And so, of course, we would cross here at 3. That would be our y-intercept. Go down 1 over 2, down 1 over 2, down 1 over 2. Hopefully I have everything drawn well enough that I can actually get a line going through those points. There we go. Wow, that's not half bad for freehanding, if you don't mind me saying myself. So this is, of course, y is equal to negative 1/2 x plus 3. Let's do the next one. Hey, why not? Let's do it in green. So of course, we start at the same point. Now, in this particular case, what's our slope? We have a rise of 3, if you want to call it that, as we go over 4. In this case, though, we're dropping. So we start at 5, we go over 4, we drop by 3. 1, 2, 3. So we go through this point at 2. We go over another 4, 2, 4, we drop by another 3. 2, 3. And that's our next point. And so we can see that we had a consistent single solution associated with our first set of simultaneous equations, because we have a single point where both of those lines intersect, and that's it. And that's the only point where we have a solution for the first line that is the same as the solution for a second line. So this is original. So original case. Now let's go ahead and look at what we're dealing with now. Let's see if I can, looks like we got a little funky. Let's see if I can do this though. Let's try to grab all these guys. And I'm just going to try to move that around over here so I give myself a little more room. There we go. So now let's go ahead and, oh, wow, that's interesting. Didn't know I could do that. That's pretty cool. Okay, but now how do I get rid of this? Oh, okay. I think I can just go back to, no, pins just changed color. So, well, let's do this. We'll just hit escape, and then I know that will get rid of that. Okay, so now let's look at our current case. So for our current case, we have the following situation. We have, of course, our y-axis. We have our x-axis. And we'll have 2, 4, 6, 8 again. And let's get that all labeled up there. And then for our, so that's our y-axis. For our x-axis, we have -2, -4, -6. We have our origin, of course. We have 2, 4, 6. And what do we have in this particular case? So it turns out that if we go ahead and resolve the equations in the form of y equals, we get y equals -1/2 x plus 3, because we didn't change that one at all. So that one just comes straight on across. On the other hand, though, for the second equation, we get a negative. Now notice we get the same 1/2 now, but we get plus 8/3, where 8/3 is equal to 3.66. So going ahead then and plotting that out, what do we get? We have, and here I can just choose some points. So let's look at -2. So if I plug in -2 here, what do I get? I get -2 times 1/2 gives me a 1 plus 3 gives me a 4. So let me make sure I'm on the right color here. Okay. Yeah, well, top one, let's go. Actually, this will be the bottom one. So yeah, let's stay with green. So then we get that point there. Then we can go ahead and propagate from that point. We go across 2, down 1, we're going to get to 3. Across 2, down another 1, we're going to get to 2. So for this particular line, and again, I'll just try to freehand this one. It should down 1, across 2, down 1, across 2. So I should get pretty close to 6 here. Let's see if I can do it. Well, got relatively close. So this particular line then, of course, is y is equal to -1/2 x plus 3. What do I then have for my second line? So let's do the second line in red. And it turns out, of course, that everything is exactly the same with the exception of the y-intercept. And the y-intercept is now up here at 3.66. And so you can see why we have no solution associated with this particular set of simultaneous equations. You can clearly see then that we have y is equal to -1/2 x plus 8/3. And so we can see that there is no intersection between the two lines. So clearly there isn't a single point at all where we have values for one line that would satisfy the equation associated with the other line. So here we can see clearly, so this is our new case. I think I'm in red, so yeah, let's just stay with that. So this is our new case, though that E didn't turn out like I wanted it. So our new case, and here we can see that we're dealing with parallel lines. And that means then, of course, that there is no solution for this particular problem, since there is no intersection. And so clearly that's what those two equations are saying. One saying, hey, you need to be on this line. The other one saying, nope, you need to be on this line. But since those lines never intersect, they are pushing you in different directions that can't be met if we're looking at this from a constraint perspective, or they're giving us information that isn't consistent. So we can now see not only from a numbers perspective, a matrix and vector perspective, what happens with an inconsistent case, we can also see it graphically and come to understand, yeah, even graphically, you can just look at it and see, yeah, there's no way that's going to work out. So let's now take a look at one last variant of this example. And so let's look at, now again, an augmented matrix. And now we're going to perfect the scalar multiplication between the two rows. So here's our augmented matrix. 1, 2, 3, 6. Okay, so I'm going to hold on to the coefficient matrix from part D. Now let's go ahead and change the constant vector. And remember that this is now 18. So here I'll say note. Now 18 was 8. So as I've already spoiled for you, I've now perfected the scalar multiplication between the two rows, not just in the coefficient portion of the augmented matrix, but also in the constant vector portion. So let's now go ahead and subtract 3 times the first row from the second row. And when I do that, clearly we take -3 times 1 gives me -3, add that onto 3, that's 0. -3 times 6 gives me -3 times 2 gives me -6, add that onto 6, I get 0. -3 times 6 gives me -18, add that onto 18, I get 0. So clearly we end up with now an entire row of zeros. So thankfully, things are not inconsistent, because if I go ahead and try to interpret what that last row means, we see that we get 0 times x plus 0 times y. Again, understanding the first column is multiplying x, the second column is multiplying y in the coefficient portion. And then for the last entry in the constant vector, that's just 0. And as I've already indicated, this is consistent. Because we get that 0x plus 0y is 0, and that's equal to 0, and that's a true statement. What else does this mean, though? This also means that the second row is essentially a repeat from an information perspective, a repeat of the first row. And so as a result, it doesn't give us So if we're relying on these equations to give us information, it turns out that that second row really doesn't give us any additional information. and trying to lock in on a particular value, or trying to impose an additional constraint on the problem. Or I will also add to the constraints. So if we're trying to lock the system down using constraints, well, that wasn't a great way of doing it because it essentially did nothing. Well, more than essentially, it did nothing, not essentially, it did nothing for you from that perspective. So that would, of course, allow us to determine a single solution. And so, of course, that means that there are an infinite number of solutions. And in this particular case, since we're dealing with lines and I have a line right on top of another line, and we'll go ahead and draw this out here in just a moment, but since I have one line right on top of another line, both of them going off to infinity, I'm not getting any benefit from that second row. If we want to pick on the second row, I'm getting no benefit from it. Now, sometimes I'll end up with a case where I have infinitely many solutions, but the solution space, we might start with three-dimensional planes for whatever we're dealing with, and we'll talk about this more in the next lecture. But we may start with three-dimensional planes and we end up with a one-dimensional line, or well, three-dimensional 2D planes that, or let's say it this way, a better way to say it, 2D planes that exist in three-dimensional space, and the intersection of those planes end up being a line. I actually got some useful information out of that. I may not have been able to come up with an exact solution, but I can clearly see that I went from these two-dimensional planes that were representing my constraints from my information, and I ended up with a one-dimensional line. So at least my solution space had a lower dimension than what I was originally starting with. In this case, it didn't do me anything. I have a line that I started with, and my solution space, or I started with lines, my solution space is a line, one-dimensional information, one-dimensional solution space. It didn't do me any good. Okay, so there are infinitely many solutions. So when we get infinitely many solutions, please understand that you have to evaluate the solution spaces as well to see if it did you any good or not. In this case, it really didn't do us any good. So here I'll say, which can be seen from the first row, because the second row is always consistent. All right, I can plug in any value for X, any value for Y, and everything works for the second row. So it's the first row that really is dictating what is happening. And so from the first row, I get 1 times X plus 2 times Y is equal to 6. And this is called, and I know I've used this term already, called the solution space. Let's put that in quotes, solution space for the system. the system of equations. There we go. Or restating it, y is equal to negative 1/2 x plus 3 is the is the most restrictive. Statement. That can be made about x and y. Now, of course, because I'm trying to tie this into this idea of I probably shouldn't put an X there. This idea that we have infinitely many solutions. Of course, as we know, the equation of a line can be satisfied by infinitely many points, infinitely many combinations of values of x and y. So since this is the equation of a line, and anything that satisfies that equation will satisfy the equation associated with the second row, because again, I can plug in any x and y values and it will satisfy the equation associated with the second row. Since this is the equation of a line, any of an infinite variety of x values yield infinite got a little wacky with that S. Possible y values. Therefore, there are infinitely many solutions. And we can see that with these linear equations, that has to be the case, because I can't have two lines intersecting in more than one location. So I can only get one solution, or the lines have to be on top of each other, which means infinitely many solutions, or the lines don't intersect at all, which means 0 solutions. Those are the only 3 options for these linear equations. So that's why it's important to recognize that we are levying that restriction on this discussion and on this class, is that we're dealing with these ideas of linear systems. Okay, now, of course, if we choose to start representing different things, different types of equations, parabolic equations, etc., then things can change. But in this particular case, since we are restricting ourselves to linear equations, those are the only 3 possibilities: one solution, infinitely many solutions, or 0 solutions. And so hopefully you can see that. Now, one thing that I want to introduce here, because it is very convenient albeit it's a bit trivial in this very simple case, but it's a very convenient way of looking at these particular types of solution sets that have infinitely many solutions, because it gives us the ability to talk about them a little bit with a little bit of specificity. Though not for this particular case, because of course I have two lines right on top of each other. And so my solution space isn't at a lower dimension than the original entities that I was dealing with. But with that said, I can at least introduce the process and we can talk about it a little bit. So here I'll say that this can also, so typically when we have infinitely many solutions, we want to introduce parameters. So I know I mentioned that at the very beginning of this lecture. So I'll say that this can be shown parametrically. And how can we do that? Well, let's just go ahead and introduce a parameter. Here, I'll just introduce a very simple one. Y is equal to U. So U is now my parameter. And then we can, of course, see that U is equal to -1/2 X plus 3. We can rearrange this. U minus 3 is equal to -1/2 X. And then we can say that X is equal to -2U plus 6. And of course, this can be seen graphically. Y, our y-axis, our x-axis. Here I'll just plot 2 and 4. Oh, let's just do 6 and 8. Why not? Since it looks kind of bare up there if I don't do that. So 2 and 4. -2, -4, -2, -4, X. And so going ahead and we can plug in that y equals 1, which means U is equal to 1. Plugging in U equals 1 into this expression right here, clearly we get -2 plus 6 is a +4. So when Y is equal to 1, we come over here to 1, come on up here. Oh, sorry. There we go. So Y is equal to 1, U is equal to 1, X is equal to +4. So we come over here to, oh, what am I doing? I got negative signs on both. That's something was looking funny. Sorry about that. Let me get rid of those negative signs. And so then we come over here. Y is equal to 1. Oh, and then I'm still on black. That's okay. I can draw over it with the screen. There we go. Y is equal to 0, U is equal to 0. We get X is equal to 6. And then that traces itself right back on through. There we go. To when x is equal to 0, u is equal to 3, and y is equal to 3. So there we go. We get that particular line, 1x plus 2y is equal to 6, otherwise known as 3x plus 6y is equal to 18. And they're one and the same lines. So since those lines lie right on top of each other, clearly that means that whatever solution I have for one line will obviously satisfy the other line, and I get this infinite solution set that has the same dimension as my original entity that I was, or my original entities that I was dealing with, of course, which I started with S lines. So when we look at the dimension of the solution space, we can see that the number of parameters that are required to capture the solution space. Here, I will admit, substituting in just for y itself seemed to be relatively trivial, but what we can do is, understanding that u is a parameter, v is a parameter, w, whatever parameter sets you want to use. As soon as we understand that it takes one parameter for us to capture what's happening with this solution space, then we can say it's a one-dimensional solution space. If we require two parameters, it would be a two-dimensional solution space. And we can start to understand the nature of the original entities. Maybe if we were lucky, they were planes and I ended up with a single parameter solution space, then I'm down to a one-dimensional solution space. And working with those particular equations actually did me some good. Whereas here, I have one-dimensional entities, I have a one-dimensional solution space because I have one parameter, and working with those expressions did me no good. I had no new information, effectively no new information that was associated with one equation versus with having those two equations. Now, one thing that I do want to mention is that there are a couple different things, a couple different notes that I want to make here at the tail end. Note number one is what? Here we have had, or we've allowed the constant vector to take on whatever values, whatever constants we want. And so when we look at what we call these linear equations versus something called a vector space, we have to recognize that these linear equations can have whatever value they want for the constant term itself. But when we start looking at vector spaces, we cannot. We always have to have zeros associated with the constant vector. In other words, when we start looking at vector spaces, and this is a bit further down the road, when we start looking at vector spaces, we need to ensure that the constants that would be associated with these linear equations are not arbitrary, they are zero. And we're already familiar with that because we gave that case a special name. Note. When solving, and remember, that's the case, the special case, the homogeneous. when solving the homogeneous form of this system. So here's the kicker, or one of the kickers. When we are working with the homogeneous form, again, we'll soon find that that's a requirement for vector, what we call vector spaces. But we also just did what? We took all of the lines and we slid them to the origin, because remember, the constant term was what? That's the y-intercept. And so if we take the constant term and drive them all to zero, that means that we have one y-intercept and only one y-intercept, which is y equals 0, when we're working with the homogeneous forms of these equations. And so guess what? Unlike the case where we had two parallel lines giving us inconsistent information, once we deal with the homogeneous form, that case is off the table. We can't have it because all of our constants, it was the constants that were pushing the lines off of each other. And now we're saying that those constants are all the same. They're all 0, which means that we always have a solution, which is the origin, when we're looking at the homogeneous case. And so then we only have two remaining cases. We have a single solution, and that single solution, of course, would have to be 0, right? Because everything is converging at the origin. So if we have a single solution, that single solution is just going to be 0, 0, 0, 0, 0 for however many dimensions you're dealing with. The other case is that we have infinitely many solutions, albeit the solution space may have a reduced dimension compared to the original entities that we were working with. Okay, so nonetheless, though, let's go ahead and dive into this idea of the homogeneous form of the system. So here we have 1, 2, and we'll just, of course, stay with the most recent version, 3 and 6. Yeah, I'm just going to stay with the matrix form. I'll go to an augmented matrix here in just a second. X times y, X times y, X and y. And then we have our homogeneous form 0 and 0. So there will always be a solution. We can never be inconsistent when we're dealing with the homogeneous form of the system of linear equations. So here I'll just say that equating to the 0 vector makes this homogeneous. What do we then have for our augmented matrix? And then for the augmented matrix, we have 1, 2, 3, 6, 0, 0. And we have 1, 2, 0, 0, 0, 0 in our row echelon form. So of course, we only have one row of non-zero values. Then parametrically, we can see something pretty interesting. So we have 1x plus 2y is equal to 0. And if we do the same thing, if we let y equal u, that's a very simple parametric substitution, then that of course means that x is equal to negative 2y, which is equal to negative 2u. And then reframing this for our solution space as xy is equal to negative 2, 1 scaled by u. So this is our solution space, or can be used to represent our solution space. We can see that we have a one-dimensional constraint, namely, we're dealing with this 1x plus 2y is equal to 0 as our constraint or our information, depending on how you want to look at it. Then the coefficient vector for our parameter u, it turns out that it is orthogonal. It spans the rest, and we'll define spans more formally later in this class. It spans the rest of this two-dimensional space because it is orthogonal to the non-zero row vector in the row echelon form of the coefficient matrix. And of course, this can be seen very simply by, as we talked about in the first part of this review, by taking the dot product of those two vectors. My row vector, 1, 2, my column vector that I will now frame as a row vector. So I'll use the transpose of it, and dot, this is a dot product, is equal to, so 1 times negative 2, that's just negative 2. 2 times 1 is just 2. And remember, we have to add those two together, and that's equal to 0. Therefore, they are orthogonal. In that two-dimensional space. And so we can see then how all this is coming together, and how now we're looking at the dimension of the original entities that we were working with. We're looking at the dimension of the solution space, and then we're looking at how they relate or how these different collections of numbers relate to the overall space in which we're representing all of this happening. So, of course, we're going to see much more of this as we continue on with this review. Again, this second review goes quite a bit longer than the first review. And it will span, speaking of spanning, it will span multiple lectures. But I want you to start seeing these themes that are coming into play here. This idea of solution spaces, this idea of infinite numbers of solutions versus one solution, and in the case of a non-homogeneous system of linear equations, that we can even have an inconsistent set of equations where we have no solutions. And then when we do have an infinite number of solutions, the properties associated with the solution set and what some of the, I don't want to say properties, but what the geometry of that solution set is telling us about what's happening with other aspects of the overall space that we're working in. So with that, I will call this particular video lecture a wrap.